It's pretty wild when you stop and think about what's really going on inside your computer. I mean, right this second, there are literally millions of invisible conversations happening. So let's pull back the curtain and take a look at the hidden world that makes everything you do possible. So here's the big question, right? You've got all these different pieces. The brain, which is the processor, the memory, your keyboard, your mouse. How in the world do they all talk to each other? When you click on something, how does that one click instantly tell all these different parts what to do? There has to be some kind of system, some kind of infrastructure in there. And there is. It's called a bus. And honestly, that's the perfect name for it. The best way to picture it is as a digital highway system, a super fast, perfectly organized network of roads connecting every single part of your computer. But here's the thing. This isn't just some single-lane country road. Oh no. This is a massive, multi-lane highway with 3 very specialized types of traffic, each with its own specific job. We're talking about the address, data, and control buses. Understanding these 3 is the key to everything. Okay, first up, the address bus. Think of this lane as the GPS for the whole system. It doesn't actually carry any of your files or data. Nope. All it carries is one thing, a location, an address. When your processor needs a piece of info, it puts the specific address for that info onto this bus. It's basically shouting out, hey, I need whatever's at 123 Main Street. Right, so once the address bus has pointed to the right house, we need a way to get the stuff from that house. That's where the data bus comes in. This is the lane for the cargo trucks. This is what actually moves the goods, the numbers, the instructions, the bits and pieces of that video you're watching. This is the pathway for the actual information itself. And finally, we have the control bus. Now, you could argue this is the most important one of all, because this is the traffic control system for the entire highway. It's the traffic cop, managing the whole flow. It sends out commands like, okay, memory, get ready to read the data at that address I just sent, or, all right, I'm about to write some new data to you now. It prevents crashes and makes sure everything happens in perfect sync. So let's break this down. What's really fascinating is the direction of the traffic flow. See, the address bus is a one-way street. The CPU is always the one dictating the address. But the data bus, that's a two-way street. It has to be, right? Data needs to flow from your memory to the CPU to be worked on, and then back from the CPU to memory to be stored. This difference is absolutely critical. Now, you've probably heard tech people talk about the width of a bus, measured in bits. It sounds super technical, but it has a huge impact on your computer's power, especially that address bus. So what does it actually mean when someone says a bus is, say, 32-bit or 64-bit? Let's make this really simple. Imagine our address bus is only 3 bits wide. It just has 3 tiny little lanes. The number of unique places it can point to is calculated with a simple formula, 2 to the power of n, where n is the width. So 2 to the power of 3. That's 2 times 2 times 2, which gives us 8. A 3-bit bus can only find 8 different spots in memory. That's it. Okay, but now let's scale that up to something real. An early computer might have had a 16-bit address bus. Using that same formula, 2 to the power of 16, that gives you 65,536 unique locations. And that right there shows you the incredible exponential power of bus width. Every single lane you add doubles the amount of memory your computer can talk to. All right, so we've got our highway system figured out, but what language is all this data speaking as it's flying down these buses? It's not English, that's for sure. It's something much more fundamental to how computers work. See, at their very core, computers are just a massive collection of microscopic switches that can be either on or off. That's all they know. We represent off with a 0 and on with a 1. And every single thing, every instruction, every number, every letter on this screen has to be broken down and translated into that simple 2-digit language. That's binary. Now, while the computer only truly speaks binary, we humans have come up with other systems to make it easier to manage. You can see they just use a different number of digits, or what we call a different base. Hexadecimal, for instance, is super common in programming because it's just a much shorter, cleaner way for a person to write down a long, messy string of zeros and ones. Okay, so this all makes sense for regular numbers, but what about negative numbers? How can a system that only knows on and off possibly understand the concept of something being less than 0? This is actually a really cool problem with an even cooler solution.
And the solution is to just dedicate one of the bits to be a sign bit. By convention, it's always the bit that's furthest to the left. We call it the most significant bit. The rule is simple. If that bit is a 0, the computer knows the number is positive. If it's a 1, it knows the number is negative. Simple as that. Now, there are a few different ways engineers have figured out how to do this. The three main methods are called sign magnitude, 1's complement, and 2's complement. They all use that first bit for the sign, but they handle the rest of the numbers a little differently. And as it turns out, one of these methods is the undisputed champion.
Yep, 2's complement is the king. It's the system used in pretty much every modern computer you can find. And why? Because it makes the math inside the processor incredibly simple and efficient. With 2's complement, the computer can actually use the exact same circuitry to do both addition and subtraction. It's a huge design win.
So, how does it actually work? Well, it's basically a simple two-step recipe. Let's say we want to find -5. You start with a binary for +5, which is 0, 1, 0, 1. Step 1, you invert all the bits. Flip every 0 to a 1 and every 1 to a 0. That gives us 1, 0, 1, 0. Step 2, just add 1, and boom, there it is, 1, 0, 1, 1. That's how a computer writes -5. It's simple, elegant, and super efficient.
Okay, let's zoom back out and put all of these pieces together. We've got our highway system, and we have the language spoken on that highway. So how does this all combine to create the smooth experience we get every day?
Well, it's really this beautiful combination of physical structure and universal language. The buses are the roads, connecting everything together. And binary is the language that all the data speaks as it travels those roads. This whole system, perfectly timed and managed by the control bus, is the invisible engine that drives everything from a simple calculation to the most complex game. So the next time you click your mouse or type on your keyboard, just take a second to picture that incredible digital highway system firing on all cylinders inside. It really makes you wonder, what other amazing invisible systems are quietly running our entire digital world, just waiting for us to discover them?